We can determine an acid dissociation constant for this buffer reaction. We have a weak acid and its conjugate base present in the solution. And if you take the minus log of both sides, well, we apply the addition rule for logarithms, and then this here is the pH. So we can rewrite this equation as follows. And this relationship tells us the protonation state of the acid. So at the half equivalence point, where the concentration of the weak acid is equal to that of its conjugate base, then the log of 1 is 0, and the pH is equal to pKa. And if the concentration of the acid is less than that of the conjugate base, then this term is greater than 0, and therefore the pH is greater than pKa, which is somewhere here. And if the concentration of the acid is greater than that of the conjugate base, then this term is less than 0, and therefore the pH is less than pKa, which is for this case to the left of the half equivalence point. We can also use this relationship, which we'll see is known as the Henderson-Hasselbalch equation, for a buffer that's created from a base. So what we do is replace the concentration of the conjugate base with the concentration of the base, and the concentration of the acid in the acid-base buffer with the conjugate acid. And now for the case where the concentration of the base is equal to that of the conjugate acid, we have the equivalence point where the pH is equal to pKa. And if the concentration of the base is lower than that of the conjugate acid, then pH is less than pKa, because the log term would be negative. So that would indicate this point where the solution is more acidic. And if the concentration of the base is greater than that of the conjugate acid, then this term here will be positive, and the pH would be greater than pKa, indicating the solution is more basic. Acid-base indicators are weak acids that change color according to Le Chatelier's principle. A typical example is phenolphthalein, which is colorless in a protonated form, and the color changes slowly to pink-red when the solution becomes less acidic, so the concentration of hydronium drops. So these typically have complicated chemical formulas, so a simplified form is shown here, where we have the proton and the indicator. So in an acidic environment, you have the concentration of hydronium being higher, and that drives the equilibrium to the left. Whereas in a basic environment, the excess hydroxides react with hydronium, thereby reducing the concentration, and the equilibrium shifts to the right. So the indicator basically changes colour when the pH is equal to pKa. And in the case of this indicator, that's equal to around 9. So if you consider a weak acid strong base titration, we expect that the equivalence point has a pH greater than 7. So this is a good indicator to use to estimate the pH of the solution. So what you do is add a few drops of the indicator in a titration, and then choose an indicator that matches the pH at the equivalence point of the titration to obtain a most accurate endpoint.